Okay, so far what we've done is we've talked about basic elements of electrical circuits. Okay, what we've done is we said that there is a current. In order for there to be a current, we need some kind of a voltage source. Then we said that if there is a current, this current depends on this voltage, and then we therefore have Ohm's law. Once we had Ohm's law, then we also figured out that, hey, there is something called resistance, which is dependent on the geometry of the material, along with the fact that we know how to find the energy and power and the cost of electricity and all that stuff. But now we're going to go into figure out how to, deal with electrical circuits. Okay, so one of the first things that we need to understand is the concept of the EMF. Now, EMF is simply equal to is nothing but the electromotive force. Okay, and in order for there to be a current, there must be something that provides an electromotive force. So without which there will be no current in a circuit. Okay, the question then becomes is what are the elements in a circuit that are responsible for an electromotive force? And those are, simply a battery or a generator. Okay, now you can think of a battery or a generator as something like a charge pump. Okay, and what it does is it essentially makes sure that charges can move around the circuit. The electromotive force essentially is responsible for supplying potential energy to the charges. Okay, so basically increasing the potential energy of the charges as it moves around in the circuit. And this so we can, the electromotive force itself is can be thought of as the work done on the charges per unit charge, and we measure it in units of volts. So this is essentially the same as the voltage that we've been talking about. Okay, so let us ask some questions here. Now, suppose you were given a battery. Okay, and you were to attach some kind of a resistor, some load to the battery. Now, let's say that you have a battery and you have your, you have your positive terminal and your negative terminal. Let's say this is the positive, this is the negative, and you attach this to some resistor. Okay, some resistor R. Now, if the battery has no internal resistance, okay, so if it has no internal resistance, then the voltage across the resistor is simply equal to the EMF of the battery. Okay, if it has no internal resistance, so in this case, no internal resistance. Now, what you're also assuming is that the connecting wires are all have negligible resistance, or basically we're just saying there's zero resistance. Okay, if the battery has no internal resistance, then the load, okay, the resistor ends up getting the full EMF. So the voltage across the resistor will be the same as the voltage across the battery. Now, however, in most cases, the battery actually has some internal resistance. Okay, so we can draw another circuit here with the load R. So this is the load resistance. Okay, and now I can draw my battery itself in this manner. Okay, so here my battery has an internal resistance of R and EMF of E, and the load resistor itself is R. So now what happens is that the voltage across the load resistor plus the voltage across the internal resistance of the battery is going to be equal to the EMF. Now, do you also understand is in this case some current I flows through the circuit. So what I know is, according to Ohm's law, I times capital R plus I times lowercase r is equal to the EMF, and this gives me the current through my resistor as E divided by R plus lowercase r. Okay, so this is the current that flows. Now, in the absence of the internal resistance, the current would end up being E divided by R. So we have this. Now, in addition to this, what we can figure out is the voltage across the load resistor, and that would be equal to I times R, and this would be equal to E times R over R plus lowercase r. Okay, We can also figure out the oh my god, what's going on? The voltage across the internal resistance, and this would be E times lowercase r. Okay, and along with this, we can also figure out the power. Okay, the total power would be equal to I times E. Okay, and this would be equal to I not E. It will be equal to I times delta VR plus I times delta V lowercase r. So the power itself would be split between the two. Okay, so essentially what this is saying is that in real cases there is an internal resistance associated with the battery, as a result of which the resistance, the load resistance, only ends up getting a fraction of the total voltage that it should get. Now, in order to get the full resistance, okay, we can make the load resistance as high as possible compared with the internal resistance, in which case the delta VR would approach the EMF of the battery. Alright, in the next one we're going to start now looking at series and parallel connections.